Module 9, Lecture B, Organizing Your Code. By the end of this lecture, you will be able to create Python files that define functions and can be imported as modules, import your own modules into other scripts to reuse code, and organize small projects into clear folders and files for easier maintenance. Writing importable modules, function-only modules. When organizing a program, it is helpful to create modules that only define functions and do not run any scripts on their own. You can think of each module as a toolbox that groups related functions such as data cleaning, visual summaries, or text processing. These modules are not meant to be standalone programs, but instead provide specific capabilities that other parts of your project can call. This structure makes each file's purpose clearer and allows you to reuse the same functions across different scripts or projects without changing them. Function-only modules help separate reusable logic from user interaction and specific tasks. For example, when working with fitness tracker data, you can place file reading, time conversion, and calculations like daily steps and weekly averages into dedicated functions inside a module. Your main script then only needs to call these functions instead of mixing logic with user prompts. This structure makes the code easier to test, more adaptable, and more resilient to future changes. Function-only modules encourage clear inputs and outputs, which makes code more predictable and easier to maintain. Each function is responsible for a specific task, takes defined arguments, and returns a result without depending on global state. In a business context, you might have separate functions for calculating taxes, applying discounts, and computing invoice totals that can be reused in different systems. As requirements change, you can update these focused functions without touching user interface code, which reduces errors and makes collaboration simpler. Python code, function-only modules. This section focuses on using a simple module that only defines functions without any script-like behavior. It shows how to import and call those functions from another file so the logic can be reused in different parts of a program. The goal is to separate reusable functionality from code that runs immediately, encouraging cleaner structure and easier maintenance. By keeping modules focused on functions, you make your code more modular and flexible. This line tells you that no additional installation commands are needed to run the script. It means the code is self-contained and does not depend on extra packages that must be installed separately. As a result, you can run the script as it is, without any extra setup steps. This helps you quickly understand that the environment requirements are minimal. The miles to feet function takes a distance in miles as its input and converts it to feet. It does this by multiplying the given miles value by 5,280, which is the number of feet in 1 mile. The function then returns the resulting number of feet so that this converted value can be used elsewhere in the program. We define a function called feet to inches that converts a measurement in feet into inches. It takes one input, the number of feet, and multiplies this value by 12, since 1 foot equals 12 inches. The function then returns the result of this multiplication. This provides a simple, reusable way to convert any feet measurement into inches in a program. The miles to inches function converts a distance from miles into inches by using 2 helper functions. It first calls a miles to feet function to change the input miles into feet. Then it passes that result to a feet to inches function, which converts the feet into inches. Finally, it returns the total number of inches as the output of the conversion. Imagine you have a Python file named distancetools.py. In the example, the text distancetools.py is stored in a variable called module name example. This simply shows how you might refer to the file's name in your code. You would use this name when importing and using the functions defined in that file from another script. This example shows how one script can import a specific function from another module. It uses an import statement to bring in the miles to inches conversion function from a file called distancetools. By doing this, the script can use the conversion logic that was already defined elsewhere. This approach supports code reuse and keeps programs more modular and organized. We start by setting a distance value of 2 miles, which we will use as our example. This value serves as the input to our conversion functions. Using it, we can demonstrate how the functions transform a distance measured in miles into an equivalent distance measured in inches. We want to find how many inches are in a distance measured in miles. To do this, we use a miles to inches function that takes a distance in miles as input. Inside this function, the miles are first converted to feet using another function, and then those feet are converted to inches. This shows how we can build more complex conversions by combining simpler functions in a reusable way. The program prints a message to the console that shows how many miles are being converted and the equivalent distance in inches. This output demonstrates how a reusable function can perform several conversion steps in sequence. It highlights how combining functions allows you to carry out a specific task, such as converting miles all the way to inches, in a clear and efficient way. This script illustrates how to use a function-only module by defining simple distance conversion functions. One function converts miles to feet, another converts feet to inches, and a third combines them to convert miles directly to inches. The script pretends these functions come from a module called distancetools, then uses the combined function to compute how many inches are in 2 miles and prints the result. Overall, it shows how reusable logic can be packaged into functions to keep code clean and modular. Naming Python modules. Clear, consistent module names are essential for keeping a codebase understandable and maintainable. A module's name should quickly convey what it does, like a chapter title that tells you what to expect. This makes it easier to find the right file without opening each one to remember its purpose. Descriptive names also improve communication and collaboration, whether you are working alone or in a team. Treat naming as a strategic part of your coding process, not just a cosmetic detail. When naming modules, use short, lowercase names and only add underscores when truly needed, so they stay easy to type and read. Consistent, predictable names make it simpler to find where to add or fix features, such as registration, scheduling, or reminders in a campus event app. As the project grows, this approach helps you organize more specialized modules, like those for data import or payment processing. It also makes it easier for new contributors to understand the structure and avoid creating duplicate functionality. When naming your modules, choose names that clearly show their specific purpose and how they fit into the larger project. Avoid very generic names that might match common words or existing libraries, because this can cause confusion and import errors. Instead of vague labels like data or analysis, use names that reflect particular experiments, techniques, or roles. Thoughtful, specific naming makes your codebase easier to organize, understand, reuse, and share as your projects grow. Running versus importing. When you split your program into multiple files, it is important to understand the difference between running a file directly and importing it as a module. Running a file as the main program executes all of its top-level statements, like following a recorded set of instructions from start to finish. Importing that same file as a module does not replay those actions. Instead, it simply makes its functions and definitions available for reuse. In practice, one file usually acts as the main script that drives the task, while the others serve as quiet libraries of tools. so the program behaves predictably in both cases. As your projects grow, it becomes important to understand the difference between running a file directly and importing it. Running a file on its own is useful when you want to see test outputs or quick feedback. But when another script imports that file, it usually only needs the functions, not the tests or extra actions. In a data analysis pipeline, for example, importing should give you tools without automatically loading sample data or causing other side effects. Thinking this way helps you move from single-file scripts to modular programs that stay clean and efficient. When designing Python files, think about who controls the program flow. A file that is run directly should act as the main entry point, handling user input, reading files, and producing output. The same file, when imported, should behave like a quiet library, exposing functions without automatically running full workflows. This lets the importing script decide which functions to call and how to coordinate them, such as in a web app where one main file orchestrates separate modules for tasks like sending emails or validating input. Structuring code this way makes it easier to test, reuse, and integrate into larger systems. Python code running versus importing. This lesson explains the difference between running a module directly and importing it into another program. It shows how code written at the top level behaves differently depending on whether the file is executed as the main script or used as a module. You learn how the special name variable reflects this difference and how to use it to control what parts of the script run in each case. This helps you write code that can act both as a standalone program and as an importable module. This line is a reminder to install any required libraries before running the script. It indicates that the code may depend on external packages that are not included by default. By checking and installing these dependencies in advance, you help ensure the script runs smoothly and avoid runtime errors caused by missing libraries. This code uses functions and objects from Python's standard library and gives them a shorter, simpler name. The goal is to demonstrate ideas clearly without bringing in extra libraries that might distract from the main concepts. Using an alias helps keep the example code easier to read and understand in this learning context. We define a function called inches to feet that converts a length from inches to feet. It takes one input, a measurement in inches, and returns that value divided by 12. This division by 12 performs the unit conversion since there are 12 inches in 1 foot. You use this function whenever you need to switch a measurement from inches to feet. This line is a top-level statement that prints a message to the console whenever the file runs. Because it is at the top level, it executes as soon as the script starts. It runs whether the file is used as the main program or imported as a module. This behavior is useful for giving immediate feedback or context when the script is executed directly, and for telling direct execution apart from import use. This part of the code checks whether the script is being run directly or used as an imported module by testing a special name value. When the script is run directly, it prints a message to indicate this and then sets a sample length of 36 inches. It calls the inches to feet conversion function on this value, which divides by 12 to get the length in feet. The result is stored and printed, showing how many feet correspond to the original inches, and demonstrating what the script does when executed on its own. We use the import library to simulate importing the current file within the same notebook. This library lets us import modules through code, which is helpful for dynamic imports or when we need more control over how importing happens. In this context, it configures the environment so the parent script is treated as if it were an imported module. This allows us to show how the script's behavior changes when it is imported compared to when it is run directly. We begin by setting the name of the current module to indicate that it is the main script being executed. This name is commonly used to identify which module is running as the primary program. Then we use the import library to load this same module dynamically. Doing so lets us treat the current script as if it were an imported module, which makes it possible to compare how the script behaves when it is imported versus when it is run directly. We call the inches to feet conversion function from the imported module using a value of 24 inches. This shows that the function can be used normally after import, while the module itself remains quiet. No extra top-level code runs during the import, so the only output we see is the printed result of the conversion from inches to feet. This script illustrates the difference between running a Python file directly and importing it as a module. When run directly, it prints a main message and executes code that converts inches to feet, controlled by a check that the special name variable equals main. When the same file is imported, that conversion block does not run, so only the top-level message appears. The script also uses a library to simulate importing itself, and then calls the conversion function for a different value, showing that importing focuses on using reusable functions without triggering top-level execution code. Importing local modules. Importing local files. As your programs grow beyond a single file, it is helpful to split the code into separate files and then import what you need. This lets different parts of your project use functions, classes, and variables defined elsewhere. Each file can focus on a specific task, such as cleaning data or performing calculations, while the whole program still works together smoothly. Organizing code this way keeps the project manageable and allows you to reuse components without rebuilding them each time. Importing a local file lets one script reuse logic defined elsewhere in the same project. For example, in a data analysis workflow, you might keep data cleaning, statistical functions, and visualization helpers in separate files, then have a main script import them to move from raw data to final reports. This pattern is widely used in areas like finance and gaming because it promotes reuse of tested components. Overall, importing local files reduces duplicated code and helps keep behavior consistent across a project. As your projects grow, importing local files helps keep your code organized and easier to manage. Instead of relying on one large script, you split your logic into focused files and import them where needed. This makes updates and fixes simpler, because changes are made in one central place and automatically used everywhere that file is imported. For example, a university scheduling system might keep all course conflict rules in a single file, so updating those rules benefits all related scripts. Overall, this approach improves code reuse and makes the structure and responsibilities within your project much clearer. Python code. Importing local files. This section explains how to treat local files as simple reusable toolboxes by importing one script from another script in the same folder. It shows how to run everything from a single place by using temporary files together with imports, so code can be organized and reused more easily. It also notes that you may need to install required libraries with the standard package manager before running the code. We begin by importing 3 standard Python modules that prepare our script for key tasks. The operating system module lets us work with files and directories. The import utilities module allows us to load modules dynamically from specific file locations. The text wrapping module helps format and manage multi-line text. Together, these imports give us the tools we need to handle files, format text, and import modules dynamically in our program. The code creates a clearly defined folder location using the operating system's absolute cath function and names it as a temporary project folder. This folder is used to store temporary module files. By relying on an absolute path instead of a relative one, the code makes sure the folder can be reliably found and accessed from anywhere in the system. The code first checks whether the target folder already exists, and if it does not, it creates it. This guarantees that the directory is available before any temporary module files are saved there. Ensuring the folder exists is necessary for the example that demonstrates how to import files stored locally. We create a local module that provides tools for converting distances using a multi-line string to hold its code. Inside this module, we define a function called miles to feet that takes a distance in miles and returns the distance in feet. It does this by multiplying the input value by 5,280, the number of feet in 1 mile. This approach gives us a simple, reusable module for distance conversions. This description explains a function that converts a distance from feet to inches. It takes a value in feet, multiplies it by 12, and uses the fact that 1 foot equals 12 inches. The function then returns the resulting value as the equivalent distance in inches. The describe trip function takes a distance in miles and converts it into smaller units to summarize the trip. It first calls a miles to feet function to change the distance from miles to feet. Then it calls a feet to inches function to convert that result into inches. Finally, it returns a single formatted sentence that reports the distance in miles, feet, and inches. We create the full path for our converter module by combining the folder location with the file name distancetools.py. This gives us a complete path that tells the system exactly where the module will live inside the temporary project folder. Having this full path is essential so we can later write the module code to the correct place and successfully import it when we need to use it. We create a new file using the converter module's path, opening it in write mode with UTF-8 encoding, so it is either created or overwritten with the correct character format. Within this file, we then write the converter module code. This step saves our distance conversion functions as a Python script. As a result, the functions can be imported and used in other parts of the project. This helper function loads a Python module from a specific file path. It first creates a specification that tells Python where the module is located, then uses that specification to create a module object that will hold the module's contents. The loader defined in the specification then executes the module's code inside this object. Finally, the function returns the module object, so its functions and variables can be used elsewhere in the script. We use a helper function to import our local module by giving it the module name and the file location. Inside this function, the import library creates a specification from the file path, then uses that specification to build a module object. The loader in the specification runs the module so its functions and classes become available. The function then returns this module object, which we assign to a variable so we can call its tools in our script. In this example, we use a trip distance of 2.5 miles to demonstrate how our imported functions work. This single value is passed into the module, so it can calculate the trip distance in different units. By focusing on one specific distance, we can clearly show how the conversion functions operate in practice. The program uses a function from the distance tools module to create a short description of a trip's distance. It sends the trip distance in miles to a describe trip function, which converts that value into feet and inches. The function then builds a formatted sentence that explains the trip distance in these units. This finished description is saved in a summary text variable for later use. The code prints a message to the console explaining that the functions it uses come from a custom module stored in a local file named distance tools inside a folder called temp project folder. This tells the user that the functionality is not from built-in features or external libraries, but from code defined specifically for this project. It helps clarify the source of the tools being used in the program. This code prints a summary of a trip distance, showing the result in miles, feet, and inches. It uses a function from a local module that was imported earlier to perform the conversion. The purpose of this print statement is to display the conversion results and illustrate how functions from a local file can be used to process and present data. This script shows how to create and import a local Python module at runtime. It builds a temporary directory, writes a module file called distance tools that contains functions to convert miles to feet, feet to inches, and to describe a trip using these units, and then imports that module with a helper function. After importing, it uses the module's functions to calculate a 2.5-mile trip in feet and inches and prints a short summary. The results confirm that the calculations come from the local module, demonstrating a practical way to organize and reuse code. How Python finds modules. When you import a module in Python, the interpreter follows a specific order to search for it. It first checks the script you are running and the directory that script is in. If the module is not found there, Python continues through a predefined list of directories, including the standard library and installed third-party packages. This search order matters because the same module name could refer to different files, and Python will use the first one it finds. When you import a module in Python, it searches for it using an ordered list of directories called the module search path. It checks your current working directory early, which makes it convenient to keep your own modules alongside the script you are running. After that, Python looks in directories where it is installed and where external libraries are stored, often managed by package tools. This setup lets your project-specific code be found first, while shared libraries are found later in the search order. Understanding how Python searches for modules is important for organizing and naming your files. If a local file has the same name as a standard library or third-party package, Python may import the wrong one based on its search order. This can lead to confusing behavior or import errors, especially when you move code between environments. By choosing distinct module names, placing files carefully, and being aware of Python's search order, you can make sure your imports behave as intended in both small scripts and larger projects. Python code: how Python finds modules. This material explains how Python locates and imports modules in a step-by-step way, starting from the current working directory and then moving through the module search path. It makes clear what the current directory is and how it fits into the overall search process. It also shows how name conflicts can occur when a local file has the same name as a standard library module, and how this affects which module Python actually imports. In this example, we point out that pip install commands are not needed, meaning the code will run using only Python's built-in modules and local files. This keeps the focus on how Python imports modules without relying on external packages. It sets up a simple environment so you can clearly see how module importing works when there are no additional dependencies involved. We begin by importing 3 standard Python modules: OS, sys, and textwrap. The OS module lets us interact with the operating system, which is useful for working with files and directories. The sys module gives access to system-specific settings and functions, such as the path used to find modules. The textwrap module is included for formatting text output, even though it is not directly used in this short code segment, and may be intended for later use. We create a new file named random.py by combining the current working directory with the file name, so it is placed where the script is running. We then open this file in write mode so we can create it and add content. Inside the file, we define a simple function called pickNumber that returns a message saying the local random module is being used. This setup is used to demonstrate how Python handles imports when a local file has the same name as a standard library module. We first import the import utilities module, then import the standard random module, but give it a different name to avoid confusion with any local module that might share that name. Using this alias helps us clearly distinguish the standard library version from any custom code. We then print the file location attribute of the standard random module to see exactly where it is loaded from. This lets us confirm which version of the module Python is using when there could be multiple modules with the same name. This code shows the first few entries in Python's module search path, which is the ordered list of locations Python checks when you import a module. By looping through the first 3 items in this list and printing them, you can see where Python is currently looking for modules. This view of the search path is helpful for diagnosing import problems and understanding the order in which Python resolves modules. We use the import library to load the random module by its name as a string, which lets us import modules dynamically when the module name is only known at runtime. After importing it this way, we print the location of the loaded random module. This tells us exactly which version Python is using, such as a local version we created or the standard library version. We use a getAttribute operation to try to retrieve a function called pickNumber from the local random module. If that function is not found, we fall back to a simple placeholder function that returns a message saying the standard random module does not provide it. By then calling this function and printing its result, we can tell whether Python actually imported our local random module or the standard library version. This script shows how Python decides which module to import when there is a name conflict between a local file and a standard library module. It first imports the standard random module and displays where it is located. Then, it creates a local file with the same name and shows that the current directory is part of Python's search path. When the script imports random again using import utilities, Python now loads the local file instead of the standard library version. Calling a function from random confirms that the local module was used, demonstrating that Python prioritizes modules found earlier in its search path, including the current directory. Preventing circular imports. When you split a program into multiple files, you need to watch out for circular imports, where 2 modules import each other directly or through other files. This can leave one module only partly loaded when the other tries to use it, causing confusing errors such as missing attributes or functions. These problems are especially common in projects where files depend heavily on each other, like separate files for reading and processing data. Understanding what circular imports are and why they are harmful is essential to avoiding them in your code base. To avoid circular imports, design your modules so each has a clear role and does not need full knowledge of the entire project. Arrange dependencies in one direction, where higher-level modules depend on lower-level utilities, but not the other way around. For example, a module that defines user account rules can use a module with database helpers, but the database helper should not depend on the user rules. If 2 modules seem to depend on each other, move their shared functionality into a separate module that both can use. This keeps module relationships clean and prevents import loops. To avoid circular imports between modules, be careful about where you place import statements. Although imports are usually written at the top of a file, If two modules only need each other inside specific functions, you can move the import into those functions. This delays the import until the function runs, so both modules do not have to be fully loaded at the same time, which breaks the circular dependency. Using this technique along with thoughtful module design helps ensure that your modules import reliably without causing initialization errors. Python code, preventing circular imports. This lesson demonstrates what circular imports are and how to prevent them using simple local files. It first shows a failing design where two files import each other and cause an error. Then it presents a fixed design that avoids the circular dependency by moving shared logic into a separate helper file. All files are created dynamically, so the entire example can run smoothly in a Colab environment. This comment explains that no extra packages need to be installed because the code uses only Python's standard library. In other words, everything the program requires is already included in a normal Python installation. As a result, there is no need to use tools like pip to add external libraries. We start by importing several Python modules that let us work with the system and manage our code. The operating system module lets us interact with files and directories. The text wrapping module helps format text so it is easier to read when written to files. The import library module allows us to load other modules dynamically and manage their caches. Finally, the system module gives access to system settings, including the search path used to find and import these dynamically created modules. We start by choosing a folder name that will store our example modules. We then check whether this folder already exists on the system. If it does, we use a tool from the standard library to delete the entire folder and everything inside it, so we have a clean starting point. After that, we create a new folder with the same name, ready to hold the module files we will work with. The write module function creates a module file with given content. It first builds the full file path by combining the folder and file names. It then opens this file in write mode using UTF-8 encoding so the text is stored correctly. Before writing, it removes common leading spaces from the content to keep the formatting clean in the final module file. We create a module called bad.a that announces when it is loaded, then imports another module named bad.b. Inside bad.a, we define a start function that prints a message saying it is about to call the finish function from bad.b, and then actually calls that finish function. Finally, we save this code into a file named bad_a.py so that the module behaves this way when it is imported and used. We create a module called bad.b that prints a message when it loads and then imports another module called bad.a. Inside bad.b, we define a function named finish that announces it is about to call the start function from bad.a and then makes that call. Because bad.a also imports bad.b, this setup creates a circular dependency that can cause import errors. Finally, we save this module definition into a file named bad.b.py in our example folder. To make sure Python can import our example modules, we first check whether the folder that holds them is already in the system path. If it is not, we add that folder to the beginning of the path list. This tells Python exactly where to look when we import the modules. Doing this is especially important for modules that are created dynamically and are not stored in Python's default search locations. In this example, we try to import a module called bad.a to demonstrate what happens with circular imports. We first print a message that we are testing a problematic design, then clear the import cache so the attempt reflects the current state of the files. When we import bad.a, it is expected to fail because bad A and bad B depend on each other in a circular way. We catch the resulting error and print a message that the import failed, including the type of error, to help diagnose the circular dependency problem. To avoid confusion from earlier imports, we remove any problematic modules from Python's internal module registry. We take the names of the modules we want to clear, such as bad A and bad B, and for each one, we check whether it appears in the current session's module cache, called sys.modules. If it is present, we delete it from that cache. This way, any future import of those modules starts clean, without leftover state from previous imports. We start by creating a shared helper module that both of our main modules can safely import. This helper module includes a print statement so we can see when it is loaded, and it defines a function called logStep that prints messages with a helper tag. By placing this common functionality in a separate module, both main modules can use it without depending directly on each other. Finally, we write this helper code into a file named shared helper, so it is available for import by the other modules. We create a module called goodA that announces when it is loaded. Then import a shared logging function named logStep from a helper module. This shared import is important because it lets goodA use a common logging tool while avoiding circular dependencies. Inside goodA, we define a start function that calls logStep to report that the start function is running. Finally, we save this module content into a file named gooda.py so it can be imported and used elsewhere in the program. In this step, we define the second module in a way that avoids circular imports by using a shared helper module. The module, called goodB, prints a message when it loads and imports a logging helper function from the shared helper. It also imports the start function from the goodA module so it can call it without creating a circular dependency. Inside goodB, we define a finish function that logs that it is calling start, and then calls the start function. Finally, this content is saved into a file named goodb.py so the module is ready to use. We begin by printing a message to show that we are using the fixed design that avoids circular imports. We then clear any cached import data so that the upcoming imports are fresh. After that, we import the module called goodB, which is part of the corrected structure without circular dependencies. Finally, we call its finish function to confirm that the modules now work together correctly, without causing import errors. This script explains how to deal with circular imports in Python by first showing a design that fails, and then one that works. In the failing case, two modules import each other, so each one waits for the other to finish loading, and Python raises a circular import error. The script then removes these modules and introduces a shared helper module that contains the common functionality. Two new modules import only this helper, not each other, which breaks the circular dependency. When this improved design runs, all modules load correctly, and functions can be called across them, demonstrating how a shared helper module prevents circular import problems. Organizing project files. Basic project folders. When you start a new programming project, it helps to create a simple, organized folder structure instead of putting everything in one place. Treat the main project folder as a container for your main script, supporting modules, data files, and documentation. This structure makes it easier to find what you need later, whether you return to the project after a break or share it with others. For example, in a data analysis project, having separate folders for scripts, raw data, and generated reports keeps things clear and manageable as the project grows. Organize your project folders to match the main parts of your work. For a web scraping tool, keep the main program and helper modules together. Store input files like URL lists in a separate folder. And save outputs, such as downloaded pages, in their own place. Give documentation and notes their own folder as well. This clear separation makes the structure easy for others to understand and helps avoid mistakes like overwriting original data, since each type of file has a defined location. Using a consistent folder structure for your projects is a powerful habit that makes maintenance and collaboration easier. A familiar layout reduces time spent searching for files and helps you stay focused on solving problems. It also lets teammates quickly find scripts and configuration files and keeps multiple projects from turning into a disorganized mess. This consistency makes backing up, transferring, and archiving projects simpler and creates a solid foundation for more advanced organization as your work grows. Separating concerns. In a small Python project, it is important to separate concerns by grouping related tasks into different files instead of putting everything in one place. You might have one file for user interaction, another for the core logic, and another for working with files or web services. Defining these boundaries early makes each file's role clear. This structure keeps the project easier to manage, understand, and share with others. You can think of each file in a project as a specialist with a clear role, such as handling input and output, performing core logic or calculations, or managing data storage. In a data analysis project, for example, separate files might focus on cleaning data, creating visual summaries, and coordinating the overall workflow. Organizing your code this way keeps responsibilities distinct, so you can improve or change one part, like data cleaning or the interface, without getting tangled in unrelated code. Keeping a project organized by separating concerns makes it much easier to maintain and expand. When different parts of the system, such as data storage and user interaction, live in their own files, you can quickly find and fix bugs without searching the entire code base. It also lets you change how users interact with the program, for example, moving from a command line to a graphical interface without touching the core logic. In real projects, like a student club app, this means handling membership, events, and notifications in separate files, which simplifies collaboration and makes the project more adaptable and reliable over time. Python code, separating concerns. This lesson focuses on separating concerns in Python by using small, focused files, each with a clear responsibility. One file handles input, another contains the core logic, and a third manages storage. Conceptually, this shows how to keep code organized and easier to maintain. Even though everything is run from a single file, it should simulate working with multiple modules that each do one job well. This line is simply a placeholder comment explaining that external libraries could be installed with a package manager if needed. In the current code, only standard libraries are used, so no extra installation is required. The comment mainly serves as a reminder for future development or for adapting the code to more complex situations where additional dependencies might become necessary. The convert inches to centimeters function takes a length measured in inches and multiplies it by 2.54 to change the unit. This works because 1 inch is equal to 2.54 centimeters. After performing this multiplication, the function returns the resulting value, which is the equivalent length in centimeters. This function saves the most recent conversion result to a file. It takes the file location of value in inches and its converted value in centimeters. The function opens the file in write mode, replacing any existing content. It then writes a single formatted line that includes both the inches and centimeters values, separated by a comma, so the result is stored in a clear, readable form for later use. The load last result function reads the most recent conversion result from a file. It tries to open the file in read mode, and if this works, it reads all the content, trims extra white space, and returns the clean text. If the file is missing and causes a file not found error, the function instead returns a message saying that no previous conversion result is available. This design lets the program handle a missing file gracefully without crashing. This function asks the user to enter a length in inches and reads that value as input. If reading input is not possible, such as in an environment without standard input, it automatically uses a default value of 12.5 inches. It then converts the input from text to a floating point number, so it can be used in later calculations. Finally, it returns this numeric length value for the rest of the program to use. This function displays the result of converting inches to centimeters. It receives the original measurement in inches and the converted value in centimeters. Inside, it prints a formatted message that tells the user how many inches they entered and what that equals in centimeters. The centimeter value is rounded to 2 decimal places, so the feedback is clear and easy to read. This program demonstrates a simple length converter while keeping each task separate. It starts by announcing that the converter is running, then uses one function to ask the user for a length in inches and read it as a decimal number. Another function converts this value to centimeters by multiplying by 2.54. Finally, a display function formats and prints both the original inches and the converted centimeters for the user. The code first sets a variable to the name of the file where conversion results will be stored. It then calls a function that saves the most recent conversion using the inches and centimeters values into that file. After the data is written, the program prints a confirmation message to the console. This lets the user know that the latest conversion result has been successfully saved for future reference. The code starts by calling a function that tries to load the most recent conversion result from a storage file. This function opens the file and reads its contents, or returns a message if the file does not exist. After that, the program informs the user that it is displaying the stored summary. It then prints the loaded text so the user can see the details of the last conversion that was saved. The script ends by calling a main function that controls the entire inches to centimeters conversion process whenever the script is run directly, such as in a Colab environment. This main function acts as the entry point, starting the workflow that collects user input, performs the conversion, and shows the result. It also saves the result to a file, and then reads it back to confirm that the data was stored correctly. In this way, all the logic, user interaction, and data storage are organized into one clear, cohesive process. This script illustrates separation of concerns by dividing user input, conversion logic, and file storage into distinct functions. It asks the user for a length in inches, uses a default value if none is provided, and converts that length to centimeters by multiplying by 2.54. The program then displays both the original and converted values and saves the conversion details to a file called last conversion. When run again, it reads and shows the most recent saved conversion. Altogether, it demonstrates modular design with a central workflow that coordinates interaction, computation, and data persistence. Small, focused files. When organizing a small project, keep each file small, focused, and responsible for a clear task, such as handling user input or managing data access. Avoid putting everything into one large script. Instead, separate related functions and classes into their own files. This structure makes it easier to understand what each part does just by its name and contents. As the project grows, this clarity helps you quickly find where specific behaviors are implemented and where bugs are likely to be. Organizing your project into small, focused files makes it easier to maintain and extend. Each file is responsible for a specific task, such as displaying questions, storing responses, or generating statistics in a web survey tool. When you need to change how something works, like the way responses are stored, you only modify the relevant file without disturbing other parts. This separation reduces unintended side effects, simplifies testing and debugging, and makes the project easier to understand when you return to it later. Using small, focused files makes code easier to reuse and share. When each file handles a clear, specific task, such as reading configuration settings, it can be dropped into many different projects with little effort. In a team, these clear boundaries reduce overlap and confusion, and for solo developers, they make it faster to start new projects by reusing existing pieces. Over time, this practice builds a personal toolkit that speeds up development and keeps projects organized. Python code, small, focused files. In this lesson, we will show how to organize a simple project using small, focused files, each with a clear purpose. One part will handle user input, another will perform the calculations, and a third will manage the reporting of results. We will simulate this multi-file structure inside a single beginner-friendly Colab script, so you can see how real projects are typically organized while still working in one place. This line indicates that you should install any libraries the script needs in order to run. It serves as a placeholder for a command that makes sure all required dependencies are available. This is especially important when the script uses external packages that are not part of the standard Python library. Overall, it is a common step to prepare the environment before running the main code. This section sets up constant values used across the program. A tax rate of 7% applied after discounts, a discount rate of 10% applied before tax, and a flat shipping fee of $5 added to the total. Defining these values as constants makes them easy to change in one place and keeps configuration separate from the program's main logic. This approach improves clarity, maintainability, and consistency in how costs are calculated. This function models how user input might be handled when calculating a purchase total. It sets a fixed item price of $20 and a quantity of 3 items. It then multiplies the price by the quantity to find the subtotal, which is the total cost of the items. Finally, it returns this subtotal as the total cost before applying any tax, discounts, or other adjustments. This function computes the final total of an order using fixed settings. It first applies a 10% discount to the subtotal. Then it calculates tax by taking 7% of this discounted amount. Finally, it adds the tax and a flat $5 shipping fee to the discounted subtotal and returns this final total. This function creates a short text summary of an order. It formats the original subtotal as a dollar amount with 2 decimal places, then does the same for the final total that includes tax and shipping. It also adds a note that the different parts of the code could be split into separate files for better organization. These pieces are joined into one string separated by line breaks, and that complete summary is returned. In the main part of the script, we first check whether it is being run directly so that the following code does not run when the file is imported. We then call a function that simulates getting the order subtotal and use that result in another function that applies discounts, taxes, and shipping fees to compute the final total. After these values are calculated, a separate function formats the subtotal and final total into a clear summary string. Finally, the script prints this summary, illustrating how each stage of the process is handled by its own dedicated function. This script illustrates a simple way to organize a project by separating input, calculations, and reporting into distinct parts. It defines constants for tax, discount, and shipping, then simulates user input by computing a subtotal from a fixed item price and quantity. The script calculates a final total by applying the discount, adding tax, and including a flat shipping fee. It then creates a summary that compares the original subtotal with the final total, highlighting how each function is responsible for a specific step in the process. In this lecture, you learn to create Python files that define functions and can be imported as modules. Import your own modules into other scripts to reuse code. And organize small projects into clear folders and files for easier maintenance. In the next module, Module 10, we will go over Final Project. Thank you for your attention. See you all in the next lecture.